Let's practice open system energy conservation with a turbine problem. So we're given that there's a steady flow of steam through a pipe containing a turbine, that it's an insulated system, and we're told to ignore potential effects. We don't know the initial specific volume. We do know the inlet pressure, temperature, radius, and velocity, and we aren't told the inlet specific enthalpy, although we'll be able to get that pretty soon. On the exit side, we don't know the exit specific volume, but we do know the exit pressure, temperature, radius, and we don't know the exit velocity or exit specific enthalpy. All right, this is a turbine. So the picture you should have in mind if you're looking down the barrel of the turbine is something like this, where a flow through the turbine pipe is turning something like a fan. So as a result of having, for example, steam pass through the turbine, the fan moves and that can do work on the environment somehow. Seen from the side view, this is what a turbine looks like. And in our case, we know that it is also a diffuser in the sense that the exit radius is bigger than the inlet radius. Not bad to have that in mind, although it's unclear whether that'll help you intuitively or not. Okay, the first step is to determine some of those unspecified variables, and we can do that using either the NIST website or the tables in the back of your book. So if you look up steam at the given pressures and temperatures, you can certainly get from the tables the inlet and exit specific volumes and same inlet and exit specific enthalpy. So I'm going to fill in those values from the tables. I encourage you to do this on your own for practice just to make sure you agree with the values I come up with. Those are our specific volumes. The specific enthalpies are here. And note the units, I wrote them in. The specific enthalpy units are kilojoules per kilogram, so if we use these in a calculation, we'll have to worry about a factor of 1,000 creeping in. Okay, let's figure out the mass flow rate. So we start with the fact that m dot has to be the same at the inlet and exit. And at the inlet, m dot I must be the inlet area times the inlet velocity divided by the inlet specific volume. Remember, velocity has years. We can put in these values. We have all the stuff on the right-hand side. So for the area, it's going to be pi r squared. We know the velocity, and we had to look up, but we have now discovered the specific volume. As before, note that I used a little more precision in the specific volume in the calculation than I did over on the left. I just didn't want to write out all those numbers on screen. Do that, and we calculate m dot equals 97.56 kilograms per second. And you'll note that I've dropped that subscript I. M dot has to be the same value at the inlet or exit. For this system, there's only one inlet, one exit, and it's a steady state. That's our m dot. I'm going to write this up in the left just so we have it for later if we need it. M dot is 97.56 kilograms per second wherever you look. Okay, so now we can potentially use this to figure out the exit velocity. Why would I want to do that? Well, I'm just anticipating that if I need to calculate the work later on and I use the energy conservation law, that I'm going to need that other velocity, but we can get it now that we have m dot. So it must be the case that m dot equals AE, VE over VE, okay, so it's the velocity over the specific volume. We can solve for the exit velocity, the one with ears, so we do that, and then we put in our values, because we have m dot and all the other stuff we already had. So we do that, and we figure out that the exit velocity must be 67.45 meters per second. So I'm going to record that over on the left-hand side where I have VE equals question marks, just so that we remember that value if we need it later. Okay, so I did that. Let's erase all this stuff now that we did the calculations using conservation of mass. From here on out, it's going to be energy. So we want to figure out what work is done. And if you think about it, this is a turbine. If it's a well-designed turbine, generally you would expect that the system is actually doing work on the environment, which means that we should have a positive value of work. We'll see whether or not that's the case at the end. The conservation of energy equation, generally speaking, is this for one inlet and one exit. So I dropped the sums, but everything else is in there. This first term on the left-hand side, that's going to be 0 because we're in a steady state. So there should not be an overall change in energy as a result of it being a steady state. Q dot should be 0 because it's an insulated system, so we'll be able to drop that. We don't actually know what's going on with Z, but we do know that GZI minus GZE, even times m dots, which are going to be the same, those two terms should cancel out. So all that stuff I circled should be completely irrelevant. On the next line, we'll just get rid of it all. So now we have that 0 equals minus W dot CV plus m dot times differences now in the specific enthalpy and in squared velocities. So let's rearrange for W dot CV. That's easy to do. And now we can just solve for it. We're interested in the work power in this case, so all we have to do is substitute in our values of m dot, the specific enthalpies, which we had the good sense to look up, and the inlet and exit velocities. We had to compute that exit velocity, but now we have it. So we put all this stuff in. All right, a lot of numbers in this calculation. One place where people slip up a lot is that extra factor of 1,000 being multiplied by the difference in specific enthalpies. The reason for that, remember, is that they were quoted in the back of the book in kilojoules per kilogram. If you want to match your units right, you better convert those to joules so that when you include that with the v squared terms, everything is in normal SI units. You don't want a factor of 1,000 floating around. Okay, so we'll reduce this a little bit. I'll keep m dot the same and just simplify the things in the second half parentheses. And sure enough, if we put all this together, we get m dot times the number 3.3 times 10 to the 5th joules per kilogram. You can see that our units are going to work out to be joules per second, which is just a watt. So we have w dot equals 32 times 10 to the 6th watts. I wrote out watts just so we didn't have another w floating around. But if it's 10 to the 6th, we can make that into a megawatt. So w dot CV is 32.3 megawatts. We see that indeed, as predicted, the work power is positive, so that tells us that energy is subtracted from the system. Normally people worry when energy is subtracted from the system, but remember, for a turbine, that's a good thing. That means that the energy has gone into the environment to do some sort of work out there, which is exactly what you want.